National Medical Entrance Exam. Okay, we are going to be a little bit fast. I will not really give you the answers, like the values. So I will have to guide you. Then you calculate the answer yourself. Okay, before putting it. So let's just continue. Okay. So the first question of Physics 2020, that's question 76, it asks you to say the SI unit for work done on an object is, okay, work done on an object is measured as, work done on an object, okay, is measured as, um, work done can be measured as force times distance, okay, and the unit of force is the units of work done, okay, is the joule, which is the same as the newtons times the meter, and the newton is kilogram meters per second squared times meters, which is going to give us kilogram meters squared per second squared. Okay, that's the that's the unit of work done. So the answer there is kilogram meters squared per second squared, which gives us the option of A. All right. Question 77 says which of the following physical quantities are all scalars? Okay. A scalar quantity is a quantity that has just direction. Okay. Sorry, it has just magnitude. While a vector quantity has both magnitude and direction. Okay. So in this case, the weight of an object is always a vector. It's a vector because it has a direction, acts always downwards. Alright, temperature of course is a scalar, mass is a scalar, and displacement of course is a vector. Okay, speed of an object is a scalar, while the velocity is a vector. So if you want to follow that, alright, the answer there is going to be none of the above. Okay, because the first three have weight. Okay, and weight is a vector. So which one has all scalars? Okay, so the answer there is E. 78. Which of the following statements about a moving body is not true? Is not true. It says A says whenever the speed of the body changes, the velocity also changes. When a body is, which of the following statements about a moving body is not correct? Okay, the one that they asked me is not correct. It says whenever the speed of the body changes, the velocity also changes. Yeah, because in fact speed is the magnitude of the velocity. Okay, so if you are talking about the changing of the speed, it means practically you are talking about the magnitude. All right, and the velocity, what makes speed different from velocity is that velocity has a direction. So if you have a change in speed, you can equally have a change in the velocity. Okay, but now this is for maybe for an object that is moving in a circle. Oh, sorry, that's for linear motion. Okay, but for linear motion, sorry, we see that the speed, okay, can be remain constant, but the velocity is changing. All right, but when you have a change in speed, you can have a change in velocity. All right. B says if the body has a constant speed, it is possible for it to have an acceleration. No, it's not. Yeah, it is possible for a body to move at constant speed and have an acceleration. For example, a body that is moving around in a circle, you can have a constant speed, but you have centripetal acceleration. For example, the planets, okay, let's say the planets that are orbiting the sun, you can say they move at fairly constant speed, okay, but their velocity, okay, is going to change because they continuously change, of course, change direction. And another thing is that acceleration, okay, it depends. The acceleration that is found there is what causes centripetal acceleration because the object is moving in a circular manner, okay, and does not necessarily have to do with the speed. Okay, so C says if it was put to rest, okay, it is possible for the body to start moving when the resultant force acting on it is zero. Okay, And this says even without acceleration of the body, its speed may change. Alright? Yes. The speed of a body, no, it's not possible for the speed of a body, okay, to, it is not possible for the speed of, they say even without acceleration, so it's not possible for the speed of the body to change without acceleration. Okay, without an acceleration, it's not possible. So the answer there should be D. All right. Then 79 says that a body X, okay, a block X of mass 3 kilograms accelerated from rest by a force of 5 newtons for 2 seconds. So this body is accelerated from rest, so mean that its u is equal to, let's say ux is equal to 0, okay, but it has a final speed which you don't know. Next question. Says 80, says since an electron carries a charge of magnitude 1.6 times 10 to the negative 19 coulombs, how many electrons pass through per second when it carries a current of 1.00 milliamperes? Okay, so we know that the charge of an electron, of course, is 1 times 10, but we know charge is given by IT. Okay, charge is equal to IT, and we can also calculate charge as M times E. Okay, so if we equate these two, you see that IT should be equal to NE, and so N should be equal to IT divided by the electronic charge. Okay, so they said since an electron carries a charge of magnitude 1.6 times 10 to the negative 19, how many seconds? So the time is going to be 1 second. So our current is 1.0 times 10 to the negative 3 amperes times the time is 1 second divided by the electronic charge is 1.6 times 10 to the negative 19 coulombs. Alright, so you can compute that and you have your answer. Okay, but this is how you're supposed to do it. Charge is the same as IT and charge is the same as N times E, so you can equate the two. Alright, and you know what? Distance per unit length of a copper wire has a value of 7.63 for a diameter of 1.450 millimeters. Okay, this corresponds to the resistivity of. So we already know that resistance, okay, of the material is given by its resistivity times the length on the area. Okay, this is the formula. But now they said in the question that the resistance per unit length, so meaning that they are going to give you R on L. So if I want to rewrite this equation, I can write that R on L equal to resistivity on cross-sectional area. Okay. So here they are going to give you the resistance per length. So they are going to give you R over L, and then they said it should for a diameter of 1.450 millimeters. This corresponds to the resistivity. So they are going to give you this one, okay, in the question. So the resistivity can be given as R over L now, okay, times A, because I'm going to give you all of this. All right. So it's simply going to be equal to, remember, area is the same as pi diameter squared on 4. So the resistance here is per unit length is 7.63. Okay. Yeah, 7.63. No, it's supposed to be ohm per meter instead. Okay, it's supposed to be ohm per meter. So 7.63 ohm per millimeters, ohm per millimeter. Okay, so it means that it's supposed to be ohm per millimeter, and millimeter is equal to 10 to the divided by 10 to the negative 3 meters. Okay, yes, 10 to the negative 3 meters times the area, which is pi diameter squared of 4 pi. The diameter here is 1.450. Okay, times 10 to the negative 3 divided by 4. Okay, squared. Sorry. A pi diameter squared on 4. So I think if you compute that, you're going to come out with an answer. They say the resistance per unit length of the copper wire has a value. Okay, so it's supposed to be ohm per meter. Okay, ohm per meter and not meter per ohm. Okay. Then next, you can compute that. Okay, you have your answer. Compute that and have your answer. If you have any problem, you let me know. You can always write down in the comment section. Please try to share the videos to your other friends that are not watching, and then you can also like, okay, share, you comment. All right. Now, the 82 says an ideal gas expands isothermally and absorbs a quantity of thermal energy equal to 500 joule. Okay, the amount of work done during the expansion is, okay, the amount of work done during the expansion is. Now we know that delta Q, there's the first of thermodynamics is that delta Q equal to delta U plus delta W. Delta W is the change, like the amount of work done on or by the system. When the work done is done by the system, okay, delta W is positive. And when the work done by the system the work is done on the system, delta W is going to be negative. Okay? So why? Because delta W is equal to P delta V, and delta V is final volume minus initial volume. So when work is done to compress the system, okay, you see that the final volume is smaller than the initial, so it's obvious that the delta W should be negative. When the system expands, when it does work, okay, it's going to expand, and so the final volume will be greater than the initial volume, and we're going to have a positive value. But delta U is the change in the internal energy of the system, and delta Q is the amount of heat entering, or the change in the amount of heat that goes into the system or leaves the system. Okay, so if it's going to the system, it's going to be positive. If it's coming out of the system, it's going to be negative. So here we have, they said 82 says that it expands isothermally. Now, one thing you should know is that delta U depends solely on temperature. Okay, and so if you expand that isothermally, so an isothermal expansion, okay, delta U is going to be 0. That's an isothermal expansion. Okay, there's what we call the adiabatic process. Okay, it occurs. Adiabatic process occurs without in a system where heat does neither enters nor leaves the system. Okay, so we have the in an adiabatic process, the delta is the one that is equal to 0. Okay, and in an isovolumetric process, okay, in an isovolumetric process, delta W will be equal to 0. Okay, so here in this case, they said that an ideal gas expands isothermally, so delta U was equal to 0. So all the energy that was supplied to the system, okay, went to give energy for work to be done for expansion. So the answer there is going to be 500. Okay, it's supposed to be 500 newtons. Okay, they said an ideal gas expands isothermally and absorbs a quantity of thermal energy equal to 500 joules. So the delta Q is 500 joules. Okay, the amount of work done during the expansion is, okay. So from the equation, delta U is equal to delta Q, the change in thermal energy is simply equal to the work done. Okay. Next, 83. A gas sample has a volume of 1.5 times 10 to the 5 millimeter cube at a pressure of 3 times 10 to the 3 times 10 pascals. Its new volume when the pressure is reduced by half at constant temperature will be what? Okay. Now we usually know the equation PV equals to nRT. Okay, PV equals to nRT. Now they are telling you that the temperature is constant. Okay, temperature is remain constant, the pressure is half. So we usually say pressure P1 V1, okay, is equal to P2 V2. Right? We have this relationship. Normally, when we want to include temperature, P1 V1 on T2 should be equal to P2 V2 on T1. Alright, but here we can do this. So we know the initial pressure. Okay, we know the initial volume. So now they said the P2 has been halved. Okay, meaning that this is V1 equal to P2 has been half, the pressure has been half, meaning the initial pressure is now, the P2 is the same as the initial pressure on 2. So I'm going to have P1 over 2, okay, and of course V2, which implies that P1 is equal to P1, okay, and I'm left with V2 equal to 2 V1. So the volume is going to double instead, right? The volume is going to double. So instead of 1.5 times 10 to the 5 meters cube, we are going to have 3.0 times 10 to the 5 meters cube. So the answer there is going to be C. Okay? It's very simple. Just a simple relationship between the two. Okay? Then the next question, that's 84. It says, which of the following statements about the potential energy and the force of two molecules is not true? Okay? And the force of two molecules is not true. It says that potential energy and force at infinity approach zero. Okay, B says the potential energy is small at equilibrium separation. C says the potential energy and force are equal to the equilibrium separation, and the equilibrium position, the force between the two molecules is zero. So they are asking for which of the following statement is not true. Okay, it's not true. Asking for which of them is not true. Okay, so for two molecules, not so the potential, all right, against separation, against the separation curve in metal. Now we have a graph like this. Okay, now at R naught, okay, at R equal to, as the separation equal to the equilibrium separation, okay, that's where the potential energy is minimum. Okay, the potential energy is minimum at that particular point, okay, at the equilibrium separation. But for the force, okay, the force, again, if you plot the graph of force against the separation of the molecules, you see that, okay, the force is zero, okay, at the equilibrium separation. Alright, the force is zero at equilibrium separation. There is a difference between this graph and this one, so you take note of that. Okay, but after the equilibrium position, so if you have R greater than R naught, the force becomes attractive. Okay, it now becomes attractive, and before if you have R less than R naught, okay, the force becomes repulsive. Okay, the force becomes repulsive. Alright, so R greater than R naught attractive, R less than R naught repulsive. But at equilibrium position, the force is going to be zero, and the potential energy is going to be minimum at the equilibrium separation. Okay, so let's read the options again. This potential energy and force at infinity approach zero. Okay, yes, they are going to approach zero at infinity. Alright, as R increases, okay, and becomes infinity, the force and the potential energy are going to approach zero. Okay, then we have B says the potential energy is smaller at the equilibrium position, okay, which is that the minimum value is at equilibrium, and C says potential energy and force are equal to the equilibrium separation. No, okay, they are not equal, alright, to the equilibrium separation. So the answer there is C. That's the incorrect one. D, the incorrect answer. D says at equilibrium position, the force between the two molecules is zero. Okay, from the graph you can see. 85 says the height to which a liquid rises, okay, in a vertical open-ended capillary tube due to tension depends on, right, the formula for the height, okay, which a liquid is going to rise due to its surface tension, right, is going to be given by 2 as the surface tension cos theta, okay, divided by the density times G, alright, that's acceleration to gravity, times the radius, okay, of the capillary. Okay, so it depends on the tension, depends on density, and of course density is mass over volume, so it means it should depend on the volume, and the G is a constant, and R is the radius of the capillary. Okay, so the answer there is going to be C. Okay, it's going to be C. Answer is going to be C. The temperature difference. The temperature difference. It does not depend on temperature. That's what the formula gives us. It does not depend on temperature. 86. What is the strength of the electric field halfway between two particles, each carrying a charge of plus 2 microcoulombs, separated by a distance of 0.10 meters? Okay. So I have two charges, plus 2 microcoulombs and plus 2 microcoulombs. The distance separating them is 1.0 meters. Okay. So at this point here, we have, if you place a test charge, okay, so at the midpoint, the distance from here to here is 0, is going to be equal to 0. Sorry, this one was 0.1 meter. So from here, the distance from here is going from each of them is going to be 0.05 meters. Okay, 0.05 meters. Right, and the force between them, remember, is going to be a repulsive force. Right, it's going to be a repulsive force. So the resultant, if you were to place a test charge at this point, okay, the force on the test charge is usually positive. Okay, if I was to place a test charge here, the force on the test charge due to, let's say this is A and this is B, okay, plus on this test charge due to A is going to be acting in this direction, repulsive, FA, and the force on this one is going to be equal to FB. Okay, so the resultant force here, FA, should be equal to so FR should be equal to FA minus FB, okay, which should give us K times plus 2, K plus 2, that's 2 microcoulombs times Q, okay, divided by the R squared, okay, 0.05 squared minus times U 0. Okay, the resultant force is going to be equal to 0. 87. The core of a transformer is laminated to reduce. Okay. Now the lamination, because of the electric field changes. Okay, because as current is being lost. Okay, the current that is lost due to that effect is called eddy current. Okay, it's called eddy current, and so the core is laminated in order to reduce, not to avoid. Okay, but see now hysteresis losses is due to saturation of the magnetization. Okay, magnetization of the core, and that's why we then instead within the core we can use silicon. Okay, within the core in order to reduce hysteresis losses as a result of the magnetization. Okay, so meaning that you are going to have some energy loss. Okay, when the thing is magnetized and in the reverse process. All right, just like we have the hysteresis loop in rubber. Okay, so we go to question 88. It says the effective capacitance of a series of capacitors with capacities 8.0 microfarad, 16 microfarad, and 32 microfarad. Okay. Now these capacitors are in series, and capacitors in series behave like resistors in parallel. So it means that the R total, C total equal to 1 on C1 plus 1 on C2 plus, 1 on C total equal to 1 on C1 plus 1 on C2 plus 1 on C3. Okay? So what we do is, 1 on C total should be equal to, since they are in series, okay, we take 1 on, the first one is 8.00 microfarad, okay, plus 1 on 16, 1 on 32.0 microfarad. Alright, so the LCM here is going to be, the LCM is 32. So 32, it means I'm going to have 32 divided by 8, 4, by this is 2, and by this is 1. So I'm going to have 8, I'm going to have 4 plus 2 to give me 6, okay, plus 1 gives me 7. Alright, it's going to give me 7. So 1 over C total should be equal to 7 divided by 32.0 microfarad. Okay, so C total should be equal to 32.0 microfarad divided by 7. Okay, equal to, you can punch and have the answer. Okay, but I think that the answer should be around 4 point something. Okay, should be 4 point something. So that's A. 4.57. It should be around 4.57. Okay, because 7 goes into this 2 4 times. Okay, remainder 4. Okay. 89 says the energy stored in a 10 microfarad capacitor carrying a 100 microcoulomb charge is, okay, carrying 100 microcoulomb charge is, now the energy stored in a capacitor E, okay, can be given as half CV squared, okay. It can also be given as if I replace, remember that cure is equal to CV. So if I was to replace, and from here C will be equal to cure on V. So if I was to replace C with cure on V, you see I'm going to come to half cure squared, sorry, V, half cure V, okay, half cure V. So if I replace this one in the place of C, I'm going to have half cure V. Or if I was to replace V, okay, V will be equal to on C. So if I replace it here, right, I'm going to have half cure squared on C. Okay. So depending on which one you have, you can what you are given, okay, you can be able to your energy. So the energy stored in that 10 microfarad capacitor, okay, carrying a 100 microcoulomb charge is, we are going to use this formula, half Q squared on C, because that's what they have been given. So if we have the Q squared, Q is 100 times 10 to the negative 6 squared divided by 2, that's the capacitance is 100, or 10, okay, 10 times 10 to the negative 6, alright? So you can be able to compute, okay, compute and come up with the answer, right? But I think that the answer should be around, anyways, just compute it, right? Compute it with your calculator and come up with the answer, okay? So next question, that's question 19. Okay, question 19. Which of the following is a property of uniform electric field? The property of a uniform. Once they say an electric field is uniform, it means that the E field, the electric field strength at all points in the field is the same. Okay, if they give you there's 2 plates, okay, they give you the potential difference between them to be V, okay, and then they give you the distance to D. So if it's a uniform electric field, it means that E will be equal to V on D. So the electric field strength at all points is going to be the same. Alright, so I think the answer there is D. Okay, that's what they mean by a uniform electric field. So the answer is D. 91. Okay. '91. So if the number of turns in a solenoid is doubled without any change in the length of the solenoid, the self-inductance of the solenoid will be what? Okay. So what is the what is the induced EMF? Okay, in a solenoid. Remember, a long coil. Okay, is given by E equals, according to the Faraday's law and the Lenz's law. Okay, E will be equal to negative divide, you can put it as VA, okay, that's the electric field strength, and E as, okay, NDI dt, okay, and also be written as NDI dt. So here the current is not changing, so I'm not going to focus on this, so I'm going to look at here. When number of turns, okay, if I change, even using this one, once you double the number of turns, okay, the double, Alright, it's supposed to double. So they said if the number of turns in the solenoid is doubled, okay, without any change in the length of the solenoid, the self-inductance of the solenoid is also going to double. Right? That's it. 92. When an alternating current voltage is applied to a capacitor, okay, no power is consumed because the current. Now, in an inductor, okay, in an inductor, the voltage leads current by 90 degrees. Meaning that the phase difference between the angle and the current in an inductor or so this is why the voltage omega t, where omega is the same as 2 pi, right? Why its current is going to be given as I naught, okay, sine omega t. Now in a capacitor it is the opposite. Instead it is the current that is leading the voltage. Okay, it's the current that is leading the voltage. The reason they said the voltage are because the current and the voltage are out of phase by 180 degrees. No, okay, the phase difference between the voltage and the current, okay, is pi on 2. That is, they said the current and the voltage are in phase. No, okay, the voltage and the current are in phase in the resistor. Okay, in the resistor. That's where you have. So they say 90 degrees, and this says that the current in a capacitor is going to be leading the voltage by 90 degrees. Okay. Then 93 says that the energy stored in a 5 millihenry inductor when a current of 6 amperes passes through it is, okay, energy of an inductor, okay, energy stored in an inductor is equal to, is given by half I squared times L, okay, half I squared 6 amperes squared times the length, which is 5 times 10 to the negative 3 Henry. Okay, 5 times 10 to the negative 3 Henry. You can compute that and you have your answer. Okay, that's the formula. Question number 94. How often would a 10 Henry inductor have a reactance or impedance of 2000 ohms? Okay, now there is what we call capacitive reactance, okay, and inductive reactance. That is the resistance current flow, okay, offered by the capacitor and the inductor respectively. So the inductive reactance, okay, XL, is given by 2 pi f, that's the frequency at which is resonating. The frequency at which is changing in the at which the alternating current is functioning, okay, times the length, times the inductor, okay, times the inductance of the inductor, okay, which is going to give. So they are asking for the frequency in this case. So frequency should simply be equal to XL over 2 pi times L, and XL here is 2000, okay, on the question, divided by 2 pi, okay, times the inductance, which is 10 Henry. Okay, so you're going to obtain, okay, where we say that the period of a single pendulum is double when its length is increased by 0.6 meters. Okay, so the period of a single pendulum is this. Now it is double when the length is increased by 0.6 meters. So the original length plus 0.6. Okay, is that. Now I replace my 2 pi with L on G. Alright, equal to 2 pi root L plus 0.6 on G. Okay, and so this will imply that 2 pi root L equal to L plus root L plus 0.6. Okay, because 2 pi will take care of 2 pi and 1 root G will take care of 1 root G. And from here you can compute it, the square both sides, you have 4L this way and L plus 0.6, and then 3L will equal to 0.6 and L equal to 0.2 meters. Alright. Then we saw 98, okay, which of the following statements is true? It's a thermometer is a device that can measure the amount of heat loss from the body, and I said that the thermometer can measure the amount of heat loss by the body indirectly, okay, but the device that is used to measure the amount of heat, okay, in the body is the calorimeter, okay, it's a calorimeter, and but directly you can use it, because temperature, okay, measures the degree, the degree of heat, okay, which is found in the body, is called the temperature, and so you can use the thermometer to measure it. All right, indirectly. So heat is a form of energy that is transferred only because of a difference in temperature. No, okay, because two bodies can be in thermal equilibrium. Okay, two bodies can be in thermal equilibrium, and they transfer heat between each other. Right, they are the same temperature. They transfer heat between each other, but there is no net heat transfer between the bodies. So this particular thing of thermal equilibrium will explain the rest of the options to you. So the answer is going to be A. 99. They said conduction, convection, and radiation are methods of heat transfer. Okay, which of the following statements is true about energy transfer methods? Okay, energy transfer methods. Now, the radiation, okay, conduction and convection always need material medium, okay, for them to be able to take place. But radiation does not necessarily need a material medium, okay, to be for the transfer to take place, alright? So A is wrong. Okay, so I'll go for D. The movement of energy through these processes requires material support. Okay, they require material support. But remember, radiation does not necessarily it means that whether the material medium is present or is not present, you are still going to have transfer of energy. Okay, still going to have transfer of energy. Then number 100, we are going to be discussing how a galvanometer can be converted into an ammeter. It says a 5 ohm resistance ammeter deflects at full scale where the current is flowing through it. The value of the resistance necessary to adapt it to measuring a current of 5 amperes is. Alright, so what we know is that if you want to convert shunt, and a shunt is a resistor of very small resistance. Okay, so you have I, which is the total current in the circuit. So if this is a galvanometer, for example, you are going to have Ig, a current that will flow through, then you connect it in parallel, okay, with a shunt, which is a resistor of very small resistance. Okay, so here I'm going to have Is, okay, the I that is going to flow through the shunt. So the principle that we're going to use here is that the voltage, I've seen that in fact the voltage across the galvanometer should be equal to the voltage across the shunt. So mean that I of galvanometer, R of the galvanometer should be equal to I of the shunt, resistance of the shunt. Okay, and from here you can calculate anything. And one thing you should know is that the total current in the circuit is always equal to I of shunt plus I of G. Because most of the times in the equation you'll be given the I of the galvanometer. So what you have to do is that you have to take the total current minus the I of the galvanometer to have the I of the shunt. Okay? So from here you can be able to do the calculation. So here the value of the resistance necessary to adapt the measuring the current of 5 amperes. So the current that should be flowing, the I total should be 5 amperes. The one through the full scale deflection current through the ammeter is 50 milliamperes. Okay, 50 milliamperes. So it means, so what they're asking for is the resistance of the shunt. So R of shunt should be equal to Ig RG divided by I. Now I of the galvanometer is 50 times 10 to the negative 3 times its resistance, which is 5 ohms, divided by I of the shunt is going to be 5 amperes, okay, minus 50 times 10 to the negative 3 amperes, okay, which is going to give us 0.05 ohms. Alright, so this is going to be I of the shunt. Now, for you to convert a galvanometer, okay, into a voltmeter, what you need to do is that you connect the galvanometer in series, okay, with what we call a multiplier. Alright, connect it in series with a multiplier. So have the galvanometer here. Current flow in the circuit is going to be I, and then here is going to be a multiplier, and that's a resistor of very high resistance. Okay. So here, the principle used here is that the current that is going to be flowing through the galvanometer will be equal to the current that is flowing through the multiplier. Okay, and we know from V equal to IR, Okay, that I should be equal to V on R. That's the voltage, okay, of the galvanometer on equal to the I, the voltage through the multiplier divided by the resistance of the multiplier. Okay, this is a principle you're going to use. You have to convert a galvanometer into a voltmeter. And when we have this, okay, we should also always remember that the voltage across the total voltage in the circuit V will be equal to the voltage across the galvanometer plus the voltage across the multiplier. Okay, so if you have this in mind, you can be able to solve any question that comes on that. So with that effect, we are done with the physics of 2020. All right, for the concours. Maybe later on we are going to look at another year. We'll take another year of physics and then we're going to solve together. All right. Thank you very much for following. See you later. Okay, please you help share a link of this video to your other friends, okay, so that they can be able to watch it out. You can put it on your status actually, and then we are going to discuss on the other aspects of the concourse later. All right.